So good afternoon. It's my pleasure to welcome you to the Charles C. Jones Seminar Series. My name is Lee Lind. More importantly, I'm delighted to introduce our speaker today, Aidan Tuohy. Aidan comes from Cork, County Cork in Ireland, and went to, now forgive me, was it? University College of Cork. And majored in electrical and electronics engineering as an undergraduate, then went to University College Dublin, where he majored in did his thesis in the area of power systems engineering, went to the International Energy Agency and worked there on analysis related to accommodation of renewable and intermittently available electricity sources, and then for the last 3 years or so has worked at the Electric Power Research Institute, EPRI, and Aidan lectured in my energy systems class yesterday, and we very much enjoyed having you with us, and welcome you to Thayer School and look forward to hearing what you have to say.
Okay. Thanks, Lee. Thanks, Lee, and look forward to presenting here. So I'm going to talk today about some of the issues around variable renewables, the integration in particular of wind and solar PV, which are the main two forms right now. Two topics in particular I'll touch on, the issue of power system flexibility, which anyone who's been kind of following this area will have heard a lot about flexibility as being a key enabler of renewable integration, and then some of the issues around operating under uncertainty due to the uncertainty, particularly around wind and solar PV, how much wind you might have in the following day, things like that. So I'm going to try and touch on some of the industry experience that we currently have had over the last 5 to 10 years as there's been deployment. Some of the work we are doing at EPRI. EPRI is a non-for-profit, utility-funded R&D company that's funded by about 90% of US utilities, about $400 million a year in funding, and a very small portion of that goes to this renewable integration issue. So I'll talk a little about some of our experiences, some of the kind of lessons learned, and some of the solutions that may be possible and interesting areas that need further research. So variable generation, as I said, we are seeing increased levels worldwide. Germany is probably at the last year or so the poster child for increased wind and solar. It's now got about 60 gigawatts of wind and solar on a system that has a peak demand of not much more than that. So it's potentially, there's some days in Germany when half the energy comes from wind and solar, maybe more. Spain is something similar. They've got days when they've had 80 or 90% of their energy. In general, Western Europe, with probably the large exception of France, has had a lot of wind and solar coming on. France is a largely nuclear country, hasn't had as much. Then here in the US, you've got the California system, where they've got extremely ambitious targets, 1/3 of their energy coming from wind and solar by 2020, maybe 2022. They've obviously been doing a lot of work and have a significant amount of experience and how to build that out, and probably as an example is probably closest to this area in terms of how their system works. Pacific Northwest, Texas, even around here in New York, the Midwest, there's a lot of wind and solar coming on and expected to grow significantly. And then on the island systems, which tend to be a little bit more unique because they're small and they have to manage everything themselves, but they still have a lot of interesting things to tell us about the large systems. Ireland has about 20% of its energy in a year coming from wind and can sometimes have up to 50% of energy. Hawaii is something similar. So there's a lot of areas that we've lessons learned and that we're expecting to see significantly more. There's been significant amounts of study work done to make sure we're able to take and accommodate those. From the perspective of wind and solar, the three key characteristics that really differentiate them from most traditional sources, from coal, gas, and nuclear and hydro, are their variability and uncertainty. So most of the other generation is both controllable and very steady. It'll do what you want it to do. Solar and wind, as we know, don't do that. On a larger time scale, a larger area, they can be a little less. They can be a little more certain and a little less variable. So there is things you can do to manage that. I'll talk a little about those. The inverter-based, non-synchronous aspect of them, which tends to impact specifically on things like voltage and frequency performance of the system and the real electrical engineering aspects of the system to maintain reliability. Again, they're connected through power electronics. They don't have large spinning masses the way a coal generator or a gas turbine might have. And then another thing about particularly the solar that's been coming on in Germany and California and places, They're not all connected at the traditional high voltage level where most generation's connected, where you're on the transmission system operator can see everything that's happening and control everything that's happening. A lot of them are on the distribution system, which are regulated differently from a policy standpoint. They're controlled differently, and they make it a lot harder to actually operate the system, or could potentially make it a lot harder if we don't think about things in advance. So we need to study these impacts and then identify some of the mitigation that's needed. So from a variability and flexibility, which are kind of two sides of the same coin, this is a graph, and I'm going to show a few of these types of load and wind and solar graphs. This is a graph from the Irish system. The first weekend we reached a 50% instantaneous penetration, Easter weekend. People get the day off. So the blue line here shows the load on the system as it was over 3 days. So load varies as you'd expect as people get up in the morning, turn things on, turn things off in the afternoon, and then in the evening again with lighting and things. The green line there shows what they had forecasted the wind to be from a day ahead, so 12 hours ahead or 24 hours ahead of time. They said this is what we think the wind is going to do. And then the red line is what the wind actually ended up doing. So you can see there it does a pretty good job of forecasting, but sometimes there's pretty significant error, particularly in the end of that Sunday. You get about a 400 megawatt error that they just had to correct for instantaneously when it at 6 o'clock they realised, hey, we better correct this forecast. That doesn't sound like a lot, but it's on a system of about 4,000 megawatts or 2,500 megawatts average demand. So it's deciding whether or not I should put a generator online, which has cost and it imposes some cost on the system. The purple line there shows the instantaneous penetration, and this is probably the most interesting one of those. So what that shows is if you look at about 9 a.m. on Sunday morning, you've got pretty much zero energy coming from wind. And you've got all your gas generation, some coal generation, and imports from the UK and Ireland is on the Irish system. Then you get through, over the course of that Sunday afternoon, evening, and early Monday morning, the wind starts picking up considerably, and pretty much all of the installed capacity at the time, which was about 1,000 megawatts back then, started coming online. So you got a lot of wind onto the system. That meant that you started having to take other generation down offline, which can have impacts on that generation. If it's going to be constantly moving around, it can have mechanical impacts. It also meant they still had to make sure that if the wind went away, they had something available to respond. And actually on the Tuesday, if you were to continue on here, the wind went back down and they needed to bring back on their gas turbines. So you got a pretty significant amount of variability on the system, and it's a high penetration. This is the Irish system. It's going to be different if you looked at a larger area like California. You won't see that variation as much, and you'll have some wind and some solar. So there's going to be different things happening in different systems, but it does show why you might have some concerns. Last thing to say about this, the Irish system have currently, and it's steadily increasing over time, but they've currently limited their penetration level. It's about 55% now. It was 50% at the time. And you can see they're even being a bit conservative there by capping it at 48. But at 48% here, or 50% in general, they stop more wind energy coming on. They start feathering blades on the wind energy. And that's because from a stability perspective, they're worried that if there was a generator tripped out of the system, then if there was a problem at a generator and went offline, the frequency on the system would change so significantly that you could end up having blackout or having some significant problems. So they limited it at the time to 50%. It's now around 55%. They're hoping eventually to get it to a 75% as kind of the target maximum instantaneous penetration. So what you do with the rest then is you either spill it, store it, or export it, and they've looked at all three and are investigating different ways to think about it, or maybe use it for a heating load or something like that. So there's plenty of other things you could be doing instead of using it for pure electricity demand.
How big is the area that's described?
So this is the entire island of Ireland. So it's 300 miles by 150 miles, something like that is the distance. Actually, sorry, this may be the Republic of Ireland. So it's most of that, but not the north, just because that's the way the data was presented. Similar things are happening in the north, but it's going to add or subtract a few percent. Give another example of one of these curves. What's started to be called, and some of you may be familiar with this term, the duck curve. You can kind of see there, if you look at the red line, why they're starting to call it the duck curve. It's somewhat got a shape of a duck, especially if you just look at the right-hand side of the graph. But what it is essentially is if you look at the blue line, it shows what the Italian load was in 2010 on the first Monday of August. The yellow line shows what it was in 2011, and then the red on 2012. So you can see this massive change between 2011 and 2012, and what happened there was a lot of solar started getting put on people's rooftops. So their electricity demand then goes significantly down in those time periods, and you get this what's called a duck curve, and that causes a few problems. You need to be able to ramp your system down and pull your system from being operating at a high level down, and you weren't used to doing that, especially in the middle of the day, so you've changed the kind of operating mode of some of your generation. You need to be able to push your generators a lot further down than you used to have to, because they now have to reach a lower minimum generation level than they ever did, and so that's again a concern about the system, where some of these generators, coal generators, can normally operate at 60, 70, 80% of their installed capacity at their lowest, but now they've had to be pushed down further, so it's retrofitting generators or causing more mechanical stresses on them. And then the last thing is you start needing to be able to ramp up quickly when the sun goes down and the load is still high. So all three of these kind of show why solar, even in more than wind, might actually cause significant problems if we don't have the right mix. So what all that means is we need operational flexibility. Flexibility is here. What I'm thinking of flexibility here, there's lots of ways to think about it, but it's the ability of the system to be able to deploy its resources to manage those changes in what we call net load, which would be load minus wind and solar. There's multiple aspects there. The wind will obviously drive some of it, but the load itself, we've always needed flexibility. It's always been in the system. The wind may increase the need for that or may not, but we need to be able to think about how that changes. Things like transmission may or may not limit how much flexibility you can get. If there's not enough transmission to where your flexible resources are, that could cause problems. And then we need to ensure there's enough. And so in the short term, that's generally done by what's called operating reserves. So a system operator carries some reserves where they back off some generation specifically so it can be moved up, and then also make sure there's enough to be moved down on a kind of a 5-minute, 10-minute hourly basis. And the longer term, though, over years and decades, you want to make sure you've got flexible resources on the system, and this is resources that can do this. And there's a few different types of resources. So on a system context, you've kind of got those balancing resources on the right-hand side, and this includes things like conventional gas turbines, hydro generation, possibly even nuclear, if nuclear is able to ramp up and down, which some of the newer technology may be able to. And then things like energy storage, demand response, and other electric vehicles and things like that could be used to balance the system. On the other side, you've obviously got the variability and uncertainty coming from wind, load, solar. Generator outages are another source of uncertainty, things like that you've got on the system that you don't really know tomorrow what's going to happen. In the middle, though, you've got a lot of things that try and facilitate or limitate that. So how your power markets are designed will either allow you to access more of that flexibility and do it at a more economic and more reliable fashion, or it might, if it's not well designed, stop you from accessing that flexibility. How you operate and plan the power system, similarly, if you're operating it using some advanced modelling tools, if you're planning using some more advanced risk-based methods, then you're more likely to have a more flexible system than if you do something in a very traditional deterministic fashion. And so you might not have as much flexibility if you don't do your operations and planning in a meaningful way. And the last thing is the grid infrastructure. The actual power system, the transmission and distribution grid needs to still be there to be able to access those resources. In most cases, obviously there is the option of just going offline altogether and having some kind of microgrid, but that is a different source. I'm talking mainly here about large systems and how they might accommodate renewables. What that does, though, then you've got these different balancing resources. So on the conventional side, the big concern around balancing resources is baseload generation cycling. You've got increased wind, and that's going to increase the variability on the system. That means then that you do have this cycling on and off of generation. So what the graph on the right shows here is a graph from a company called Abtec, who've done a lot of studies in this area, quantifying the cycling impacts of cycling coal plant or gas turbines. And what you see here is that obviously the more of the actual, the colder the generator is before you start it up, the more damage it does. So if you're having to put generators in and out of cold state over multiple weeks, then that's going to cause significant damage. But even doing it from a hot start, or even this, the LL here being load leveling or load level, if you're moving those generators around a lot, you start getting damage on them. So parts start breaking down, you start getting wear and tear, and you're having to do maintenance more often. You may end up reducing their lifetime as well, or reducing their efficiency. So these are all things you have to think about when you're operating the system. Well, which generators do I really want to cycle? Because some are more designed to cycle than others. The Irish power system, to go back to the earlier example, the coal generation on the Irish power system has been designed to cycle frequently because it's on an island system. So when they went and bought that coal generation, they made sure it could cycle. Most of the coal generation here in the US doesn't operate that way. It was designed to be plug and play. You put it on, you just leave it on. A lot of them don't even have good control systems to the system operators. They have to be called up. So depending on the particular generator, you may or may not want to cycle it frequently. And if it's at the end of its life, it obviously doesn't matter as much if you're going to be cycling it because it's going to be retired anyway. But if it's a generator you were hoping to get another 20 years from, that might be a problem. You do get curtailment of wind, and I already spoke about one of the reasons, which is kind of getting down to that we can't take any more wind on because we want to keep some generation online, and we can't turn that generation offline. That can be from a stability perspective, but it could also be just because it'll take so long to turn off a coal generator and turn it back on that you don't want to necessarily wait around. It needs to be there tomorrow. So you can get curtailment for that reason. You might also have curtailment because there's not enough transmission to get the wind from where the wind is to the load. And so here in the US, a lot of the wind will be in the Midwest, but a lot of the load might be further east. You need the transmission to do that. And then you may actually want to start curtailing wind at some point, and there's been some investigation of this to say, is it worth actually curtailing some of the energy, maybe 1 or 2%, so that you don't have to cycle this generation as much? Overall, that might actually reduce cycling, or might reduce overall system costs and even potentially have some. The carbon emission impact is likely to still be negative. You'll probably have more carbon emissions if you start curtailing wind, but depending on the particular cycling you're avoiding, that might even avoid some carbon emissions as well. So there's different reasons why you might curtail, and some of them is because of this cycling. That's not to say that cycling is always bad. There's going to be times when it's always happened, and we always have cycle generation, so it might be still something we want to do. Certainly as we go forward and try and figure out what new resources are needed to manage wind and solar, making sure it's generation that can cycle at pretty much a low efficiency hit, a low maintenance hit is probably a good idea. So when we're talking about the need for flexibility, it's generation that can cycle in an efficient manner. Another piece of flexibility is demand response. Demand response is a pretty wide-ranging term, but what I'm meaning here by this is a way to control the demand, either increase or decrease the demand. You may want to increase it as well to capture more of the energy or from the wind or the sun, or you may want to shift the energy in particular, where you may be able to use something during the night instead of during the day when there's more wind available. So demand response is generally enabled by a lot of these smart grid technologies, advanced metering infrastructure on the residential side. It could be large industrial load on the other side where they're bidding into electricity markets that they can shut down their load when needed. So the types of loads are important for demand response as a flexible resource. You want to be able to shut it off. You might even need to be able to ramp it slowly or ramp an aggregate of the load slowly so that over time it starts ramping up to manage some of the wind and solar. The storage could be important, particularly in something like electric water heating. Can you wait? Can you use the electricity now and then wait another 6 hours for when people actually need the water? But you might be able to better manage some of the wind and solar. And how is it aggregated then as well? The way that it's aggregated, it can vary between anything from a utility controlling all the various devices on the system to those various devices contracting with some provider who actually tells utility, I've got this much available, and essentially acts like a conventional generation, something like a virtual power plant where they actually basically are a power plant themselves that the utility can control as such. There is such things we want to look for with demand response, though, that it's not exactly a conventional resource, and one of the big pieces are the second to last one there, the availability. That's a kind of a risk that needs to be really considered when we're thinking about demand response to integrate variable generation. There's the short-term risks and availability where we don't know if it's going to really be there tomorrow, whereas with a generator, a conventional gas turbine, you know if you want 150 megawatts, you'll get more or less 150 megawatts when you ask for that. Unless there's a problem, which there can be some percentage of the time which you manage in your operations. On the other side, with demand response, again, it's the same thing. You may or may not get it, but the issue could be far greater. It might be, well, you ask for 150, you get 250, or you get 50, and so you need to be able to trust that, and that's basically about building up experience, building up data, and building up the right control systems to make sure we get what we need and the right visibility, giving the system operator confidence so that they know when they ask for something, they get it. And they're starting to do that. The PJM system here in the US has a very wide range of demand response. About a quarter of its capacity market for 2016 cleared as demand response. So about a quarter of the capacity it's relying on for 2016 to manage its peak demand is demand response. Now, there is more conventional capacity there if that demand response goes away, so they're not too worried. But eventually, that other conventional capacity goes away. So then they get worried on the longer term. about whether or not there's enough conventional capacity on the system. If you can't trust demand response in 5 years' time, then it's really even worth not building something else, because you're going to need it eventually anyway. So again, demand response just needs a lot of trust, a lot of operator confidence, which can be built up with experience, can be built up with the right control systems, and could potentially be an extremely valuable resource. The signals on the top right here show in red what the system wants from this resource, and these are deliberately offset from each other. So this is giving exactly what you'd want. If you saw a similar signal for coal on the blue line, you wouldn't be getting anywhere close to what you'd want. It would be tracking things a lot slower. So demand response can be an extremely valuable resource if it's well thought of, well designed, and well implemented. And it potentially could be a really big enabler of some of the renewable technology. Storage is another similar resource, and in some cases it will be storage providing that demand response on the small storage, but I'm thinking here more on the larger storage. There's obviously a lot of different technologies. Pumped hydro storage is already well widely deployed and well understood and extremely valuable in those places it's available. In the United States, it's probably not available in a huge amount of more places, so we're pretty much tapped out on that. We might be able to do a little with some of the existing hydro dams and convert them with a pump back, or certainly up in Canada they can provide more pump storage that could be used in the US as well, similar to the way Norway and Sweden is being used for Germany with the wind and solar that they have, Germany and Denmark. But in general, the other storage technologies are compressed air energy storage, battery storage, various types of battery storage, a large amount of various types, and then things like flywheels and capacitors, which are really short term. There's a lot of different values of energy storage, and I do say that it's expensive and inefficient. And what I mean by inefficient here, even though the efficiency levels can be high, if you're storing wind, you're always going to lose some of it. So unless it makes sense to store some, lose some, and put some on the grid later, you're better off just putting it on the grid now, right? So unless you're going to otherwise waste it, or unless it otherwise is coming in at a time when you don't really need it, then it's better to actually to try and use it close as it's being produced. There is a lot of values though of storage. The most obvious one of wind and solar is being able to store during the night and be able to use during the day. That's probably got a lot of the value, and particularly in those cases when the wind would otherwise have been spilled because it's too high during the night and there's not enough demand. On the other side, there's also the fact that a lot of storage, particularly the battery storage, responds really quickly. So similar to the demand response signal I just showed, battery storage does a lot of the same. That's got to be important as well, because as more and more wind and solar come on the system, you're going to see more variation on those short time scales. And so having something that can respond in a very quick and accurate way is going to be extremely valuable. And in fact, that's already started to be rewarded in a lot of the electricity markets. Here in the US, the Federal Energy Regulatory Commission have mandated that all the organised electricity markets somehow reward fast frequency response and fast frequency regulation. So anything that could respond quicker and more accurately than conventional generation is now getting paid more to do so than the conventional regulation. Until then, they were all getting paid the same amount, whether they were good or bad at the job. So that's another value of energy storage, and then it provides capacity again, where there's enough capacity on the system and having enough resource adequacy. There's plenty of other values of energy storage, and one of the main challenges right now is trying to figure out what is the actual value of a given type of storage generator in a particular location on the system. Where is the best place to put storage? Is it behind the meter? Is it on a distribution circuit somewhere at a local substation, or is it up on the bulk transmission system like a large generator? There's a lot of issues need to be resolved from a regulatory and market viewpoint to figure out, well, how can we accommodate storage? Even if we can show that this is extremely valuable from a societal perspective, right now a lot of the storage still wouldn't make enough money to justify being built from a merchant perspective. So how do we change the regulations? How do we change the markets to better reflect the value? And obviously that should be done in a very technology neutral way. So it should be more valuing specific characteristics rather than valuing storage by itself. So for example, frequency regulation, the example I just gave where the new market products are coming in, it's a good example of storage is being rewarded, but it's not being rewarded because of storage, it's being rewarded because of a particular way it's actually been able to behave. So being able to do some of those things for energy storage is going to be extremely important. We need a set of standards, we need standard ways to think about energy storage to make sure it actually can be deployed in a way that's providing value to the system. So this kind of gives an example of all of the above: energy storage, demand response, conventional generation, how things might change on the system. And this is more of a kind of a thought experiment, but it is based on some real systems, places like Ireland, places like California, and how they might evolve. So this is looking at it from a value of the market standpoint, and this could be dollars, but it could also be kind of megawatts or some other value. But essentially, until recently, this is kind of before you get a lot of renewables on the system, energy was the main source of any income for the generator, for any resource, but it's also the main value on the system, providing energy at low cost, reliable energy. Some piece of your total money spent, though, went on capacity, and the capacity there is both just having something in the ground, making sure that it's there in 10 years' time or 5 years' time, and then also the transmission and distribution system. So a lot of it's just the fuel that you're burning. There's some value of just having something there for those peak days of the year in August when you need something, and so people have to pay those generators because they're not going to stay online just because of just for the energy prices they get for the few days. So there needs to be some mechanism to do that, whether it be allowing those energy prices to get extremely high for a few hours every year, or they're paying them in advance for being there in 3 years' time or 1 year's time. And then the last piece is ancillary services, which is the reserves to manage that short-term variability and uncertainty that you get, and you get more of it with wind, obviously. So how that might evolve in the system, and we don't know this is exactly how it might evolve, but it might move to something where energy, because wind and solar are zero marginal cost energy, it doesn't cost any fuel to produce energy from wind or solar. They become less important, but then things like capacity become more expensive, both because of the cost of capacity for that wind and solar, but also because you need to spend more to make sure that the capacity is there when the wind isn't there. And then lastly, the ancillary services obviously are going to become more important as well, being able to provide quick response, being able to provide accurate response when the wind and solar move around. So the kind of thought is that it'll somehow move towards something that changes the pieces of the pie. You still have, we don't know what the overall size of the pie is going to look like now, so maybe bigger, maybe smaller when you get a lot of renewables, but it's no doubt that the component pieces of that will change, so that how you actually end up paying your electricity bill might end up changing. You don't maybe pay for kilowatt hours anymore. You might end up paying something for kilowatt hours and something for kilowatts, depending on what your demand is. And it might still be that your total bill is cheaper, but it might be that the way that bill is split up is different. It could be that if you have a solar resource, you're actually paid to provide some of this, but you still need to pay that other component because it's providing some of these other things to help support the fact that you put solar on the grid. So that's kind of the idea of having more flexibility and how we might get that. The flexibility here would fit under both capacity and ancillary services. Flexibility, from a capacity point of view in the future, you might not just want the right number of megawatts to meet peak demand, you might also need a certain type of megawatts to be able to ramp around the place. So you may end up having to pay for flexible capacity, and in places like California, they're already starting to think about how that might work. So then operating under uncertainty, that law looked at the kind of planning context, what kind of resources we might need, how they might fit together, what type of flexibility we might need to manage that. From an operations perspective, if we do have a certain set of resources, how do we operate the system on a kind of a daily basis? And this is something that we've been doing a lot of work at EPRI on, trying to figure out how we can use new methods to think about operating the system. And then also on the planning timescale, you might want to start planning for uncertainty, which I kind of mentioned already. So responding to variability here, what this kind of cone-shaped thing is doing here is basically coming from the day-long things that you have to think about a day ahead of time, right down to the almost real-time instantaneous stuff on the right-hand side. And on the kind of y-axis here, the size of the cone shows how much variability and uncertainty you're looking at when you're making decisions in those timescales. So if you look at it from a day-ahead perspective, you think there's a lot of variability, a lot of uncertainty, but you got a lot of stuff that you can manage that with. So you can think about it, well, what do I have to make a decision on now that I don't get a chance to come back and revisit later? So I might have to say, well, this coal generator should stay offline or should come online. So generally it's things like what generation should I have online or offline. But you don't have to worry too much about things like quick start generation, battery storage and things like that, because that will be there for you. As you get in closer to real time, 4 hours to 30 minutes in this example, you start getting less variability and uncertainty. So we know better 4 hours ahead of time what the wind is going to do or whether or not it's a cloudy day than we will know a day ahead of time. So you get less variability and uncertainty, but then you also have less decisions that you can make to manage that. So your space of decisions isn't as big. So what you can do then is maybe start up some generation that's still warm and that's just after being turned off. Or you can maybe start thinking about things like, should I charge my energy storage? Should I start notifying people that we're going to want them to change the way their water is going to be heated for the next 6 hours because we think we might need them in 4 hours' time, so can they charge their water heaters now instead? That type of thing. And obviously then you might need price signals to do that, or you might need some other type of signal to start sending those types of things out. And then as you get into 30 minutes and 5 minutes ahead, really what you're trying to worry about is, do I have enough generation online right now or other resources that can respond if something happens between now and 5 minutes ahead? This is still in the time frame where people are making decisions themselves. System operators are looking at it and saying, should I do something more? Should I increase the amount that I have? Should I ask gas generation to back down? And then as you go from 5 minutes to 10 seconds, the uncertainty and variability gets smaller again, but really then you're left with things that are just automatic control functions that generation can respond in an automatic time frame. And then as you get down to the very end, you get very little variability and uncertainty, but really all that can happen on the system is the real instantaneous stuff that generators automatically give you. You don't have a chance to ask it to do anything. So that's kind of the time scale of getting down closer to real time. One of the things here that obviously as you get more wind and solar, this envelope gets bigger, and it gets a lot bigger on the left hand side but not much bigger on the right hand side. So you want to try and make as many decisions as close to real time as possible. So one of the big efforts right now is trying to say, well, we should be making decisions closer to real time when we have more information and better information, and also more frequently. If we can make that instead of having to do something if you, for example, got rid of that 5 minute decision making there, you'd have to make all that decision at the 30-minute time scale. And that's what they do in a lot of systems. Traditionally, they might only decide every 30 minutes and then leave everything be automatic from then on. And that's because it was easier. It was because the computing power and communications technology may not have been there. But now we've got that type of computing power, that communications technology, so it's worth putting that online. So really trying to make decisions closer to real time and more frequently will significantly help accommodate a lot of the variability and uncertainty without having to install any new devices, without having to do anything like that. Another piece with increased uncertainty, this shows the challenge that's faced by some system operators. This is an example from Denmark, where they're looking 48 hours ahead. They've got on the red line, you've got an aggregate, or you've got an average forecast that says this is what we think is going to happen with the wind. But you also got this spread of uncertainty in the blue. So they don't know whether it's, and they looked here up to 90 percentile, so 90% sure it's going to fall in this range. So this is a nice graph that shows what the uncertainty they have to do. So they have to be able to make sure they can manage that type of uncertainty with whatever plans they make ahead at a time. We've been working on tools that can actually take stochastic optimization techniques, and quite a few people are working on tools and methods to take those techniques and be able to come up with actual answers then that say these are the generators we should be putting online, this is the operating reserve that you should be carrying to manage that generation. So using these kind of stochastic optimization, using the uncertainty is going to be important. We'll never be able to predict, obviously, as you know, the weather day ahead. You always are going to have uncertainty in that. You can improve it. Right now, the average errors says they're 8 to 10% for a wind farm or 4% for system. That's coming from German data, but it's probably similar in most places. That's the average error, though. On a given day, it might be far more. So as you can see there, around hour 40, the error in the hour 40 area there, the black line side is actually what turned out to happen. So sometimes even it does go outside that 90th percentile, but in that area is very significant, so it's a lot more than 4%. And that came at a bad time because it came at a time when the wind was changing. So even though we might have a very low average error, there can be times when you get really significant error, and that you still need to be able to cater for that. So the large ramps on the system can be extremely important, and they can be the time when your forecasts perform worse. So that then again means you need significant amounts of flexibility. You need to be able to actually access that in your operations, and you need to be able to think about how you do that when you're operating the system. So that gives a good indication of how you might actually manage uncertainty. Obviously, system operators, they've got 100 things to do, and they don't necessarily want to have to look at these types of graphs. So one of the big research questions over the next while is how do we give them the information they can make actionable decisions off, rather than giving them a spread of uncertainty where they have to spend 10 minutes thinking about something, and in the meantime 20 different alarms have come up about different power plants that are doing different things. And so they don't want to have to look at these kind of things. They want one decision that says this is what you should do, and that's generally true. Obviously some of them might have some inclination to see some of these things, but most of the time they want, let's make a decision here and tell me what I need to do. I don't want to have to be second guessing myself. Because guys in the system control room don't really have to worry about economics. They're mainly worried about reliability and keeping the lights on. They won't lose their job because they turn on an extra generator. They will lose their job if the power goes out. So unless we get them proper stochastic optimization methods, do some new research to give them tools to do this in an economic fashion, they'll always just choose the bottom line there and just say that's how much wind I'll have, and that way at least I'm not going to get fired. So the best way to do this is to start working on better techniques and tools to deal with that risk. Another piece around operations is controllability. And Germany, I've actually got quite a few slides in a minute on Germany, but this shows an example from the German power system over time. And generally what's been happening in Germany, they shut down their nuclear, which was all down the very south of the country, or shut down a lot of their nuclear, and that's where a lot of the load is. A lot of their wind is up in the north, their solar is kind of distributed across, but a lot of it's up in the northeast or some in the south. What's been happening there then is that they don't have the transmission system down the middle of Germany, so what's been happening is that the power has been flowing through France, Belgium, the Netherlands, Poland and Czech Republic, back around, and this is what's called loop flows. Loop flows are undesirable because power system operators don't expect them. The guy in France is sitting there thinking he's going to get 3,000 megawatt hours in from Germany in a given hour, and it turns out to be 10,000 because it was windier. It turns out to be negative, and they're sending power that way because it wasn't windy. If it was one person controlling the whole system, that wouldn't be a problem because they would know exactly what's going on ever in the system, but because there's different pieces of the system being controlled, these loop flows are a big problem. There is things we can do with it though, and Germany, as I said, is building transmission, and it's going to actually build a lot of high voltage direct current transmission because of the fact that it's more controllable, so it can actually send the wind directly down. They don't have to worry as much about Kirchhoff's laws and power flowing where it will. The other thing that's happening, and this is a demonstration on the right-hand side from SmartWire Grid, a company in the US that's funded out of the DOE ARPA-E program. They're these little donut-type things that you put on the end of transmission lines, and essentially they allow the reactance on the line to change. And by doing that, you can change the control the flow a little bit. You can't do full control of flow the way you would with a power electronics device, a DC line or something like that, but you can control the flow pretty well on these types of transmission lines. So, not that they're being used in Germany, something not too dissimilar called a phase shifter is being used in Belgium and the Netherlands to stop a lot of those unwanted flows through Belgium and the Netherlands. Of course, that's pushing more flow to Poland and Czech Republic, who are now going to start installing phase shifters, and you could end up having a kind of a war of attrition there where both sides keep installing more and more phase shifters to stop German wind coming through their system until Germany starts installing some transmission. But these other lines on the right are actually a cheaper way than some of the other technology, and it does a lot of the same things. So places like the Tennessee Valley Authority in the southeast, nothing to do with wind and solar, are using these to help control loop flows on their system. But eventually these kind of devices could be extremely valuable when we do have a lot of wind and solar going where it will. It'll stop some of those problems. The last piece that it could be important, and that wind and solar, there's been a lot of work on, particularly on the wind side, is around the issue of frequency response. And so we want to maintain the frequency in the system at 60 hertz. That's what all the devices, all the motors, things like that run on. And obviously as load and supply start varying, you do get changes in that frequency on a second to second, a minute to minute time frame. That can be managed by balancing the wind and so using conventional generation or storage or demand response. The top graph though shows what happens when there's a fault on the system, that a generator drops out. So if a generator has some problem and it suddenly disconnects at its substation, you get a large spinning mass on the system essentially is suddenly disconnected. So all the other generation, first of all, sees this large dip in frequency because you end up having a less stable system. It all starts coming back online straight away though then by having this large spinning mass that it has. It stops the frequency dip from going too far, and most of the time, if not all the time, you'll make sure you don't end up having to shed some load to manage the generation supply balance. Obviously, if this was taken to an extreme, you'd end up having to shed all your load, but that has never really happened from a frequency perspective. What might happen though is that you do end up having to shed a significant amount of load to get your system back online, which is undesirable. So that currently is managed by these large spinning massive generators. With wind and solar PV coming online though, they don't have that spinning mass. The wind that's on there, most of it now is connected through a power electronics interface. WFED induction generators or Type 4 generators, they don't provide inertia naturally to the system, so you can get significant reduction of that spinning mass, and then therefore you could have significantly further dip in this frequency response, which can cause more load shedding. Again, that's all undesired. And then you also don't get that quick reaction from generators called droop response, which is basically that the generators start generating at a higher level for a few seconds or minutes until everything else gets back up to speed and you get some more generation online. So because none of that happens automatically with wind and solar, and it all happened automatically with conventional generation, you could have significant problems, and that's been often talked about as one of the main limiting factors that might eventually stop 100% renewable energy. You can, though, now, and GE in particular, particularly for wind, can provide emulated inertia through its power electronics. So essentially it borrows a small bit of energy from the rotating mass of the wind turbine, pushes it back out onto the system. You do have that payback period later on, a few seconds later, where the wind then slows down again. So you do end up having a little bit different than the normal way that conventional generation provides this, but it can be done. Solar, you might need some storage to help you do that, but it can, or else you can curtail the solar a little bit, a few percent below, and then if something happens, push it on. So both of them can be done. There's still a lot of validation and testing needed to do that. It needs to actually happen, but in Texas, they've started seeing this. They've started requiring all their wind generators to provide this, and they've done some testing to show that it actually does work. So this is another factor that may have originally been seen as potentially limiting wind and solar deployment, being addressed by new technology and by some of the power electronics there. Last thing I want to talk about it quickly is the German experience. So Germany has been in the news a lot as kind of, depending on who you talk to, either an extremely positive story about how wind and solar can work and everyone is great and feeling great, or it can be the complete opposite, where if we have wind and solar we become like Germany and we end up being extremely expensive and not actually saving any carbon. And as always, the truth's probably somewhere in between. Germany's had some really nice success stories in terms of wind and solar. It's got a lot of wind and solar, and it's never blacked out. So that's number one thing that's happened. It's not less reliable in any meaningful, measurable way. But there's other things that have happened which have meant that there's lessons learned that we can kind of apply before we get to those points on the US system or other systems. So Germany has these. This shows the installed capacity in 2013. Got about 64 gigawatts of wind. Most of it's connected on the low voltage and medium side, so it's not the type of generation that people normally expect. It's even not for wind in the US, most of it's actually connected on the high voltage. So in Germany it's even more distributed. It tends to be smaller one-off type plants rather than the large plants we have here in the US. So there's been a lot of wind and solar obviously installed. As you can see there, it's 43% of installed capacity, probably somewhere like 22% of its actual energy being generated from those. Obviously, that's mainly for solar in particular because of huge feed-in tariffs, but they've started reducing those now, partly because they've gotten a lot of what they wanted up to now. They've got a ton of wind and solar now, and then partly it's because they are worried some things need a little bit more time to adapt and change, particularly given the fact that they're retiring a lot of their nuclear after the Fukushima accident, and they've had to really change the way they operate the system. The loop flows issue I mentioned with how they interact with their neighbours has been a significant concern. France, Czech Republic, Poland in particular have been very hard on the Germans to lean hard on them to change some of the way they do things. They've had to go out and upgrade a lot of infrastructure, and I'll show in a minute why, but it's been basically costing them somewhere around 28 to 43 billion US dollars, depending on exactly what they end up building. But they've identified a large amount of DC transmission, large high voltage stuff coming from north to south. But also on this local networks, they have to be fitted up to make sure they can handle large amounts of solar PV. They've also started mandating now two-way communication with the distributed solar, even the very small distributed solar. You've got a choice essentially. Either you can be communicated and told every now and again, hey, you have to curtail down a little, or else you can never be at more than 70% of your installed capacity. You can never produce more than that. So you kind of have a choice. Most people are obviously going for the first one. It costs a little bit more, but they have some communication. Some of the lower voltage stuff, it's only one-way communication, but a lot of the somewhat, even reasonably sized PV has two-way communication in the German power system. Obviously, that's an important piece, and it's, you know, using some of this new smart grid technology, we're actually able to do some of the kind of things that maybe we wouldn't have before. But that means we can get some controllability and visibility, so the system operator now knows there's a lot of solar on, or that the solar is starting to go away, maybe because a lot of cloud coming in over the country. Things like that they're aware of that they maybe weren't aware of 5, 6, or even 2, 3 years ago. This shows the deployment of renewables, which is wind and solar here on the German system. So if you were to look at a US graph here, it would pretty much track the German system until around 2006, and then Germany would just skyrocket ahead compared to, not in terms of gigawatts, but in terms of the shape. The US kind of and Germany weren't too dissimilar the first part of the decade, and by the end it was a very different matter for Germany. Most of it there, as I said, would be on that medium voltage and low voltage, which means less visibility for power system operators. It means less controllability traditionally until some of the new standards have come in place. So it does mean, again, that there needs to be large smart grid deployment to be able to understand what's happening. It's communicating, instead of communicating with a few hundred generators or maybe a few thousand generators the way they did before, they now have to start communicating with tens of thousands of generators, some of which they've not really tested and they don't really know exactly what's happening. So there's a lot of recent standard changes in Germany. So when some of that communication wasn't mandated when most of the solar went in until 2011 or so. So that's meant going back, retrofitting plant. It's meant going back, having to make significant expensive changes, doing truck rolls, having electricians go to people's houses. So one of the hopes would be that we try and in the US here, or maybe other parts of Europe, try and put those standards in place before you have to go back and address them afterwards. And the standards then are needed because you do need that communication, you do need that control to be able to manage. This shows another one of these system curves, and this shows the current PV on the system based in January. So it wasn't that all the PV was producing. There was about 28 gigawatts, I think, at the time. But as you can see, it wasn't producing nearly as much as that. But it's showing them what's going to happen as it doubles or even triples in size. And right now, it doesn't look like that's going to happen anytime soon because the incentives have been rolled back. But it's still a concern that it could happen naturally because solar costs come down and people put more solar on their roof. So these types of issues then will end up meaning that you have significant changes, and it goes back to the flexibility needs from earlier. You're going to need to be able to plant that traditionally would have come online at the start of the day at 8 a.m., stayed online and turned off at 10 p.m. Now it has to do this kind of two shifting where they'll come online and then they'll come down to accommodate that green or blue line, and then they'll have to come back online again. So again, that's new types of resources needed. Traditional resources aren't really the types that will really do the best job in managing that type of variability. And then some of the other pieces are these interconnection standards, which again are addressing these problems. So the German power system's a 50 hertz system in the rest of Europe, but they've had this problem called 50.2 hertz, and frequency deviations, large frequency deviations to 50.2 or 50.5 or 51 hertz can happen if a large amount of load is suddenly disconnected. So back in 2002 or 3 with the Italian blackout, that some of you might remember, the Italian system essentially disconnected and blacked out, but the German system stayed up, but the frequency went pretty high. It went up to 51 hertz or so because you now had less demand on the system. That was fine then. There wasn't much solar, and I don't think it was at a time when there would have been solar production anyway. It might have been either early in the morning or late at night. But if you did have the solar on there now, you now see that a lot of it actually is required to disconnect at this 50.2 from an anti-islanding safety perspective. So they don't want, if there is something weird happening in the bulk power system, they don't want people going out fixing something and then finding the solar still online, and obviously that's a big safety issue. But what is happening then, what could happen is you could get this 10 plus gigawatts of solar disconnecting, which would be far larger than anything the power system is used to disconnecting. They're used to, at worst, a large nuclear generator, a gigawatt or so, disconnecting. So that would cause significant problems where we wouldn't be carrying enough. And so there's two options there. One is to make it last a little longer, maybe go up to 51 or 52 hertz before disconnecting. There's probably an option as well, I guess, to have better communications and sensing so that the anti-island is done in a different way rather than based purely on frequency. Or you could just carry a lot more operating reserve, but that would really defeat a lot of the purpose of putting the solar on the system, which is carbon reduction. So they've started going retrofitting. As I said, it's 400,000 units that they're having to go out. Everything over than 10 kilowatts, which is a pretty small generator size. So they've had to go out to every house, make some switches. Talking to some of the guys who are in charge of the rollout, they're pretty concerned that the electricians doing it obviously don't even really know why they're doing it. So they're going out there making some turn. They're told turn something on an inverter. They've gone back out and tested and found that something like 3 and I don't know what the number, 3 and 10 or something like that is, that doesn't actually make the changes properly. So they're going to have still they still don't know if and when something large happens on the system, whether they lose a lot of this PV. So it's still going to be a big concern. It could be something that could come up in the future years. And even anyway, there's still those 49.5 and 50.5 where wind is there and sitting at that, and that's still waiting for something to happen where you could get a large event on the system and they could disconnect. So there's some things there with Germany that are being addressed in some of the stuff that's been done in the US, and I know ISO New England here are actually working through a process themselves now to come up with some recommendations, and other similar ISOs around the country, to make sure some of these issues get addressed before you get this large deployment, so that we can still have the large deployment, but you don't end up having to work through it. And the last piece of this is just one or two slides I wanted to show of why this is, how we might address some of these things. So this is a large effort at EPRI called Integrated Grid. Where we're coming at from this, a utility-funded research company obviously is going to somewhat reflect the views of its members. And for a while, the members were very concerned about loss of business, loss of revenue because of rooftop PV, which is still a concern, but they're realizing they have to come up with new models. We want to make sure that the bulk system remains reliable, economically affordable, and are sustainable, environmentally friendly, all the other things you really want from a power system. There's a few ways to do that. One way would be everyone go off grid and microgrid, which could work. It could be, but it could be a very expensive way to do it. Another is to still make sure we use the grid and understand we use it. And so the concept of the integrated grid is kind of everyone playing together and being able to make sure we have the right facilities and rules in place to understand what those technologies can do, so that we can deploy the right technologies to manage that variability, uncertainty, all the other impacts that wind and solar PV have. So this is one of those issues where, taking lessons from places like Germany, we can start coming up with a better way of doing things, both from a regulatory and policy perspective, but right down then through how you actually operate the system as well, about integrating a lot more than just traditionally, where in the traditional viewpoint of this, the left-hand side of this graph would have been completely cut off from the right-hand side with one line between them. We want to think about everyone playing together. Utilities have a place to play, policymakers and individual customers as well, and making sure you got that customer choice. So that needs this kind of various pieces: modernization, standards, and planning and operations, policy regulation. So that's a kind of something just to leave you on that I think this is an area that is going to be extremely important in the future because of these issues that are driven by things like customer choice, driven by policy, but also then has to underline that, have some of that technical and engineering expertise that informs all of that. Okay. That's
Yeah, I myself understand the system reasonably well about reactive power and control of frequency and voltage grid. Now you've got negative loads on you with switching power supplies. How do you communicate the problem to the people who control the funding to correct it?
That is actually one of the main drivers of this integrated grid effort that EPRI have launched, and it's something that we've heard from both sides, from utilities who are concerned that policymakers don't understand our problems that we're facing, but also from customer advocacy and things like that they're worried utilities are just going to say, well, let's not make any changes because that's easier for my job. I don't have to make a huge... That's the easiest thing, and it's easier for their long-term sufficiency, or for them being sustainable long-term if nothing changes, but we know that's not going to happen. So both sides have come to both sides realise that that's the case, and there has been significantly more push recently to try and understand some of these issues, and Germany's a great example of that, because not that Germany's now not to do everything, but there's certain things there they could have done a lot better. So being able to understand that and explain it, there's been significant push. I've noticed even within my company, which I think is relatively representative of the utility industry and how the utility industry thinks, to really go after trying to explain some of these things in a straightforward, simple manner that we can actually... Now, you're never going to be able to put these in a really basic manner. I think that's not the point, but I think you want to be able to at least convince people that we need rules, we need standards, we need new market products that can incentivize some of these right approaches. And it's not to say we always need the utility. It might be that the utility of the future looks very different, is a very different type of model than the utility of today, but we have to be able to actually adapt those kind of things rather than... The last thing we want is a lot of destruction of existing capital and a lot of existing utilities to just directly go out of business, which could cause huge problems. It should be an adaptation as things go through that transition to whatever the future is that we kind of want.
It looks to me like the optimal use of solar and wind is to decouple it completely from the grid and decentralize its use, and that will do away with a lot of the uncertainty that's associated with that. I wonder why that is not being promoted.
Cost. It's extremely expensive to do that. I mean, you'd be talking about fundamentally changing the way electricity is generated and delivered. And if you were to say, well, let's build a new system that we can have in 10 years' time or 20 years' time, that might be possible. But we're based on an existing system. No one's going to suddenly say, well, okay, I'm okay without power for the next 5 years as long as you come back with something better.
Cost in what context? I don't see why it would be more expensive to have a small installation on my roof compared to building a huge installation and deal with all the problems associated with companies.
The large the grid. I mean, the grid has over the years, from the time of Edison, grown because of economies of scale, right? And so, if you were to maintain reliability on your own house, you'd either need a significant amount of energy storage. Yeah. You'd need things like significant redundancy on your system, which is something that is an option. We're not saying don't do that. We're saying that, hey, that's one option, and there's probably options in the middle as well, which kind of are more microgrids that are still connected to the main system for when you potentially need them. And then there's the centralized system. The centralized system, in any studies that have been done, has always been a lot cheaper. You get the benefits of economies of scale, efficiencies, and things like that that just are very hard to beat. That's not to say they won't eventually be beaten, and certainly more and more customer-side generation is going to happen. There's going to be a lot more zero net energy type homes. But whether or not they fully disconnect from the grid is where the question becomes important, because if they fully disconnect from the grid, it doesn't really matter. They're not relying on the grid. But if you're still connected to the grid, you're relying on the grid at some point, and so you need to be able to support that grid still being there for when you need it, for when the sun isn't there or the wind isn't there, or you have energy storage and you spend a lot of money to do that.
Yeah, maybe you can answer a question. We were out in the Midwest in an area where there were lots of windmills. There were probably 100 within 5 miles. And the big farms, this is in Illinois, and the corn-growing farms had typically maybe 6 or 8 of these windmills per farm. And they're these very tall, very modern, very impressive looking. And we stopped and went out to look at them and be impressed. There was no sign of any power lines leaving them. They must have been buried, I assume. Now, would that be low voltage? Would that be medium? Can they run a more higher voltage underground?
They would have run some medium or low voltage to a substation a couple of miles away, where all of them would have been connected and presumably got out in some transmission system.
Yeah.
Then
I mean, we never could see any lines at all.
And if not, there is a possibility to underground high voltage.
And it seems to me they must have been underground, but there's a huge amount of expense in that.
Yeah.
I mean, we think of the towers as expensive, but I mean, the square mileage here was what? At least 10 miles on a side, so 100 square miles.
Without knowing about the specifics of the plant, I couldn't say why they would have done that, but it seems very strange to have done that out in the Midwest. I mean, I can understand why it might be done in a more populated area. A lot of undergrounding. Germany has a lot of undergrounding done. Denmark's actually moving all of their cabling underground over the next 10 years or so.
Well, the farmers apparently didn't want those.
Yeah, I mean, someone was willing to pay enough money to do that, then they'll do that.
There was an impressive, obviously serious dirt road
Yeah.
that was obviously the place where they buried them, and I just wondered if you knew what it looked like underneath.
I mean, I've seen underground cabling, but it would be a pretty impressive site. I'm not sure why they'd do that, other than someone willing to pay a lot of money to do that. That's interesting.
Is there any thought put into distributing power in a DC distribution system rather than AC? Obviously, that creates a lot of problems.
Yeah. In the wind integration community, the people who go to a lot of the conferences and talk to each other a lot about it, there has been discussion around, will we eventually hit a fully DC grid, and how that would look. We're obviously still not there in the technology, but even also on the kind of concepts around how we control that, it's a very interesting problem. Fully DC is probably a long way away. But what you will see very soon is, as I said, DC in Germany, the UK is doing something similar. there's significant efforts in Europe to come up with what's called a super grid, which would mainly be DC, which would, if you think of Europe and the Mediterranean, it would be at least DC connections of offshore wind, an offshore wind mesh network of DC coming into places like Germany, France, the UK, DC between there and the hydro generation up in Norway and Sweden. And then potentially even there's also another project, and sometimes they've been joined together, looking at DC connection to Northern Africa and having a lot of solar there. And the idea would be this large amount of DC being an underlying backbone. You still have your AC distribution and transmission system, but the DC would spread the power on the high voltage set aside across the continent. Again, it's a cost issue. At a long enough line, DC becomes pretty cost effective because the relative cost of the power electronics isn't as high then as the actual cost of the line, and the efficiencies you gain from DC and those long distance transmission can help a lot, and the controllability you have. But right now it's still, I guess it's not as niche as it used to be, but it's still relatively niche. There's also similar proposals in the US for.
Has the relative cost of DC versus AC remained constant over the last 20 years, or has it changed?
What I gathered is it's coming down. It's coming down pretty significantly, and likely to come down more in the future. I couldn't put numbers to it, to be honest. I've seen the graphs. I just can't think of the actual numbers.
Using Germany as a modern test bench, if you like, you had 43% wind and solar. Is that backed up with spinning reserve? Because solar can shut down like that as a cloud wave comes in.
It doesn't.
Back it up.
It doesn't have to be backed up fully with spinning reserve, because while a cloud can come in and cause solar to go down, that's only one solar panel or even plant, and so across an entire region you don't have that large change. Yeah, so you've time. It definitely does. So if you look at this graph here, this isn't the actual summer peak demand or anything like that. It's just a typical winter day. But you can see on winter you can't rely on solar at all from the long-term perspective of meeting demand without some kind of storage or demand response to shift that energy. So while on a short term you don't need spinning reserve or anything spinning, you still probably need plant in the ground or some other type of devices. And it can be local, it can be central, but you need to have some type of generation that can still make up those demand, or you have to reduce the demand at that time and use something else. Obviously wind will come in there as well, and there is going to be some capacity available from wind, but you're going to get less than what's there in solar.
Let's take one more question.
Well, I was going to ask what that was a graph of. It's not clear to me.
Okay, so it's so black line is system load in the German system in, I think, January of this past year, a few months ago. The dashed purple line is what that net load of solar looked like on that particular day with all the solar that's installed.
When you say solar load, you mean the demand?
System load, that says there. So that's the system demand. Yeah, system demand. And then what it would look like if more and more solar was coming onto the system.
And daytime is, the low is nighttime, right?
The low on the black line is like nighttime. But on that blue line there is if you actually had a lot of solar now, the low would be even lower during the day than it is during the night. And actually they're already seeing that in Hawaii, where their daytime minimum load is now lower than their nighttime minimum load in some days.
Did you have a question?
Yeah, sort of. Decoupling, one way to do that is store it.
It again becomes so there's two things to think about there. I think the first thing is if you had storage and decided to completely decouple and the cost implications of that versus being part of a larger system. You could be part of a larger system and have local storage as well, but you'd get the same benefits, but except you'd still have the benefits of being connected to the bulk system. And then it becomes an economics of, is it worth paying for that versus worth disconnecting and trying to do everything on yourself. And right now I don't think the economics are there in anywhere that's got a decent power system, but as time goes by we don't know exactly where costs are going to go, both on the grid side and on the local side. But from if we assume that it's all connected to a grid at some point, whether decentralized storage is better than central, well, it depends on the particular things you're trying to do with the storage. So A lot of the things you might want to do with storage, like shifting wind and solar, can be done both decentralized and centralized. So maybe, but then there's certain things that can be better done on a decentralized level. So if the cost implications are the same, whether or not you're decentralized or centralized, if you think of if it's just a lot of the same thing in a centralized location versus, dividing them out and putting them out in a decentralized way, then it would seem to make more sense to be decentralized. Then you're more at the source of some of the solar. I would never say that the best thing to do, even in that situation, is directly couple solar and storage. It doesn't make a huge amount of sense to say that you have to do some kind of smooth output from a solar storage combined generator. That doesn't make a huge amount of sense. You're better off putting it onto the system when it's there rather than having to lose some of that efficiency loss, because if you put a megawatt hour of solar in storage, you only get 0.8 out at best right now. So unless you otherwise would have wasted it, or unless it would have been put on at a time that wasn't very valuable, you're probably better off putting it directly on. Storage can still be very useful for other reasons and can interact directly with the grid as well. And often that, in a lot of the studies and simulations we've done, we've shown that that's a better way to do it, is just have storage as a system asset rather than have it as a directly coupled to the renewables. There's a few specific examples where you might want to directly couple it, but it's less obvious than having storage as kind of an interaction with the system and solar as a separate interaction.
i.e. it's a complex system.
Exactly, yeah.
Battery powered car. You can only use the car at night instead of charge your batteries during the day. Maybe we should shift how we work at night.
So I might mention, I neglected to mention before, that next week we're going to have Lou Fulton from UC Davis, formerly of the International Energy Agency, who's an expert in energy futures forecasting. So if you were interested in this, you might be interested in that. And let's thank our speaker. Aidan, thank you very much.